Hello guys, good afternoon again. Uh, I will be showing you how to perform experiment number 2. So experiment number 2 is about laws of motion. We have three laws of motion. Okay? The first law of motion is called the law of inertia. The second law is the law of acceleration. And then the third law is the law of interaction. So in this experiment, we'll be doing two laws of motion, the first law and the second law. Okay, on the first law of motion, we have the so-called equilibrium. And equilibrium can be translational equilibrium, and then it can be also rotational equilibrium. This setup is about translational equilibrium. Okay, so when we say equilibrium or static equilibrium, if we're going to get all the forces acting on the object, so in our case here, the object here is the dynamics part. So all the forces acting here should be zero. Okay, so we need to get all the forces, the x component, the y component, and then get the sum. The sum should be equal to zero for us to say that this system or this dynamic card is in equilibrium. Okay, so the objective of this experiment is to determine the mass of the object in static equilibrium, or specifically in translational equilibrium. So for us to get the mass of this one, we will be measuring this using the top loading, and then the other ones we're going to compute the value of the mass using the formula, which is tension over g sine theta. Okay, so we have here the force sensor. The force sensor is used to measure the force exerted, okay, or the tension in the string. Okay, so that's the purpose of the force sensor. So force sensor is from the word itself, so that is a sensor, a type of sensor, and that should be connected also to the GLX. Okay, so again, the GLX will measure the value of the tension or the value of the force. And then again, we have here the angle indicators, and the angle indicator is used to measure, of course, the angle. Okay, so in our experiment, we'll be setting the dynamics track to 15 degrees, and then after that, we're going to change the angle to 20 degrees. So we'll be using two angles here. The first angle is 15 degrees, then the second one is 20 degrees. So the target is to get the tension. And then if we have the tension, we have the angle, we can compute for the mass of the dynamics card. Okay, again, we have the theoretical value of the dynamics card that can be measured using the top loading balance. So we just need to put the dynamics track here, or I mean dynamics card. Okay, the value there is 517.67. So that is in terms of grams. Okay, but in our experiment, we'll be using the value in terms of kilograms. So 517.69 grams, that is equivalent to, divided by 1000, is equivalent to 0.52 kilograms. Okay, so that is the theoretical value of the mass of the dynamics card. Okay, so we have, I'll be writing here the value of the theoretical value of the mass of the card. So this is 0.52. And then for the 20 degrees, that is also 0.52. Now, I'll be getting the tension. Okay, the tension here can be measured by the force sensor. And then, of course, we have the given angle, which is 15 degrees. So the value of the tension divided by g sine theta. The g, again, is the acceleration due to gravity. That is 9.8 meters per second squared. So using that formula, we can get the experimental value. And then after that, we have the experimental, the theoretical. We can now compute 40% error. Okay, now let's start with experiment. Okay, so the GLX is already set to digits. Okay, that is set to decimal places. So the first thing you need to do if we're going to use the force sensor is to press the zero button here. Okay, if you want to calibrate the reading, press the zero here, and then the reading here will be zero. And then after that, I'm going to attach here the dynamics card. Okay, so what are the forces acting here? Okay, first is the dynamics card has a weight here because it has a mass. For us to get the weight, that is simply mass multiplied by acceleration due to gravity. So whatever be the mass of this one multiplied by 9.8, that is the weight of this dynamics card. And then also here we have the string, so meaning we have a tension here. Okay, we have the tension, we have the weight, and then we have a certain angle. We can compute there the mass. So the mass is simply equal to the tension divided by g sine theta. So that's the formula for the mass of the dynamics card. Okay, so let's look at the reading here. Actually, there's fluctuation because of vibration, maybe. Okay, so, but as you can see, the readings are around 124, 136, 130, 118, 1.27, 1.36, 1.39. Okay, so let's use the average or the middle. So the mid value is, if the highest is 1.39 and then there's a reading of 1.27, okay, so that's 1.33. So the tension in the string here is 1.33. I'll be placing here the 1.33. Okay, the tension as read by the port sensor is 1.33. Again, the angle is set to 15 degrees. The theoretical value is 0.52. So we'll be computing for the experimental value. So the value for the experimental value is simply mass over, so this is the formula. So tension is 1.33 over 9.8, which is the acceleration to gravity. So this is in terms of Newton. Okay, then multiplied by sine angle. So this is 15 degrees. Okay, so we have 1.33 divided by 9.8, and then we have sine 15 degrees. Okay, the answer here is 0.52. So 0.52 or 0.524, but let's round out these two decimal places. So this is 0.52. Okay, this is 0.52, this is 0.52. Obviously, the percent error will be 0. Okay, because 0.52 minus 0.52 divided by the 0.52. Okay, there's no need to compute for that. Use a calculator. Obviously, that will be 0. Okay, that's for the first angle. Now let's set the set up to 20 degrees, and let's look at the reading on the tension. Okay, it should be set at 20 degrees. Na ba siya? Okay, so the reading here is 20 degrees. So this is the angle. Now let's look at the reading on the GLX. Okay, the reading there is 1.65, 1.74, 1.68, 1.74. Okay. Wait. Okay, again, that's 20 degrees. Okay, so the reading here is 1.68, 74. Okay, I guess the mid value is 1.71. Okay, so the tension there is 1.71. This is 1.71. And then the experimental value is the same formula. We need to use this formula. So in this time, the value of the tension is 1.71. So, and then this will be sine 20. Okay, again, the answer here is 0.52. Now, on the second angle, so we have 1.71 newtons, 9.8 sine 20. Okay, so we have 1.71 over 9.8 times sine 20. Oh, sorry. This should be sine 20. Okay, sine 20. So the answer is 0.51, 0.51017, or simply 0.51. So this is 0.51. Okay, now let's compute for the percent error. So that's simply 0.51 minus 0.52. Okay, that's the difference, absolute value of that. Okay, divide by the theoretical value, which is 0.52. Okay, multiplied by 100 times 100. So we have 1.92. So the percent error is 1.92. Again, the target is simply below 10. Okay, you just need to remove the negative sign because the formula is absolute value. Whatever be the answer, so that should be positive. Okay, so this is the first part of experiment number 2. Thank you.